The standard model of particle physics. It's a model, it's not a solution, it's not a theory, it's just a model of the universe. And it is a mechanism or tool for trying to understand relationships within the universe. Anyway, it uses 19 or more constants or numbers representing some characteristic in nature. Now, the reason they are constants and sometimes a number, they can also be a number that's not a constant, it can be a range or something else. It can also be algorithms, that sort of thing. But anyway, constants are usually values that are either found a lot of places for whatever reason, they're the leftover characteristic of doing an equation. Or they can be something that is a very specific characteristic of reality. A very good example of this, I'm going to do an example involving human beings, ballistics, explosives, that sort of thing. There is a constant that every time you double the diameter of something in three-dimensional space, every time you make it from this big to this big, it's going to take up 8 times the volume. And the shape isn't really relevant, except, of course, there's always an exception, and there is one or two, but depending on their circumstances. But all things being equal, it will be an 8-to-1 ratio. Ratios like that, volume change per the other change, delta v delta, that sort of thing, these changes end up just being a damn number. Pi is just a damn number. What it represents is a constant in a two-dimensional surface of a circle, and it's the distance going around the circle reference to its diameter. And you can have it different number ways of doing it, so you're using it based on half the way around it or whatever, but you end up with that number showing up at a very simplistic level. And similar to doubling something this way will make it 8 times more volume. You have another set of numbers that show up for, if it's a 2D surface, if you double it, it'll be quadruple the surface area. And if you increase a square, if you do a square shape of a cube and measure diagonally, it's almost always 1.41, and it's some long string of numbers. These end up being constants that you end up just writing down, like the natural log, etc. There's also hundreds of these numbers that are sometimes called magic numbers, simply because they solve a bunch of problems, or they just keep showing up everywhere. And when you see the numbers show up where they don't belong, or you don't think they belong, it's a hint that you're looking at something you don't really understand fully, and you can find out that, oh yeah, that applies over here because of something I didn't know about. These act as hints for the next layer of this project of reality. You can have the gravitational constant, which we don't have nailed down perfectly for very, very many decimal places. We do, but it really isn't as nailed down as some of these. Planck's constant, the speed of light, which actually does have an actual finite value, a very precise one. A Hubble constant, the cosmological constant, the proton to electron mass ratio that tells you that they are not exactly the same weight, but you can find out what it is. Obviously, they're not the same weight. They're very different. And various masses of various other particles in relation to each other. Once you find one particle you can weigh, measure, or estimate, or whatever, and you can reference it to it, you usually pick the lightest one, but not always, for your, what is the word I'm looking for? For your unit-based thing. So you could measure everything in electron mass units or something like that. That's not a real thing. Well, that's another video. But anyway, so are we just injecting a set of discovered numbers to reflect reality? Or are they just arbitrary numbers that just reflect reality? In physics, one of them is called the fine structure constant, or Sommerfeld's constant, commonly denoted by the Greek letter alpha. Now, the reason it's called one of them is it quantifies the gap in the fine structure of spectral lines from hydrogen atom. When you look at a hydrogen atom that's been excited to a high temperature, it will produce light. You can just do this with hydrogen gas if it's pure. And the light is going, if you bring it up to the point that it's as close to white or literally white as possible, you'll find lots of little dashes or cuts in it. And these very, very fine cut-in points, or black spots, or bright spots even, are referred to in this. Anyway, that's why it's called the fine structure constant. It's related to those patterns, the spectrum. And it had been measured by someone named Michelson and Morley. And the other name it has is from Arnold Sommerfeld, who introduced this fine structure constant, or Sommerfeld constant, in 1916. This, in extending the Bohr model of the atom towards what we now have for the Standard Model and that sort of thing. That's the old method for it, and he was trying to figure out what was causing this. A fundamental physical constant characterizing a dimensionless quantity independent of any system of units. It's just a number. It's a ratio. And that number can show up other places. Between the following two things. The strength of the electromagnetic interaction between elementary charged particles. How strong the electromagnetic interaction is between charged particles. If they're charged particles, the electromagnetic field between them, not just the electrical field, what is the strength of it? And comparing that to the coupling of elementary charged particle with an electromagnetic field. How much it being altered would alter that electromagnetic field. Now, this seems like a very vague or a very obscure thing to do. Now, what does this thing end up being? Well, if you use the formula that's supposed to be used to figure out what this number should be, you wouldn't expect it to be a perfectly rounded off integer number. It shows its numerical value is approximately 1 over 137. Bunch of Rick and Morty fans just flipped out. Now, the reciprocal of it is not actually 137. The reciprocal of it is 137.035, and it goes 99913. If it was all nines, you could argue that it would be 0.036. The rounded off version, which is good enough for most activities to get a ballpark idea of things without making too many mistakes, and then you apply the proper number when you do the final equation, is that its real value is 0.07297352252, also written as 1 over 137.036. But obviously, we already have the other decimal places, so there's no need to round it off. This fine structure constant is not precisely an integer. It's approximately an integer. Stable matter, and therefore life and intelligent beings, and the ability for stellar fusion to produce carbon so that carbon-based life forms would be possible, quote-unquote, couldn't exist unless this number was perfect. But if you use the integer number 137, it can't work and nothing works. It would screw things up. It has to be this fine, detailed number that goes on for a lot more decimal places, by the way. And it's a lot like pi. You can't round it off. Dear Southerners. So anyway, no, that's just a joke on the net. Don't go for that. But it represents something that is actually a critical number to have written down somewhere. So you just write these down. It's like 1.414 is used a lot for figuring out RMS voltage versus current versus wattage versus whatever as part of the equation set. They're just numbers you plug in. But it's part of the quantum electrodynamics, or QED, which if you look that up has another meaning as well. And this is the quantum theory of the electromagnetic force and describes interactions between light and matter. And by definition, it also has something to do with time-space. Now, immediately, a lot of you who are fans of a particular cartoon I already mentioned might be thinking, well, this could, and then it's a pop subject I'm bringing up here. It is related also to the electric charge carried by a single proton or electron, given as a positive or negative number, as the elementary charge or constant of, and it's 1.602 on and on and on and on, coulombs. The conclusion that these quantities are constant raises the question of why. Why the specific value? This appears to be a fine-tuned universe. Coronavirus. Anyway, next. I'm trying out a new coffee today. Let's see what happens with my brains. Ow, I hurt my brain. Anyway, here we go. And no, I didn't cover my hands, cover anything that time, so now I got to wash the room down. Anyway, let's get on with it. Anyway, are there known values are merely an accident of the current time in which it happened to measure them? Or is it an example of a fine-tuned universe throughout time? Which gets really fuzzy because you think time-space, that kind of feeds on itself. If they were variable over time and such, it would be just an accident. If they're constant, then it must be planned or something. Or neither has to indicate some sort of planned or fine-tuned universe. However, if the universe didn't have some of these characteristics by accident, it wouldn't exist. You wouldn't have it be stable in some cases. So this brings up the obvious problem, or not a real problem. The multiverse concept is based on the idea that the universe, at the moment of boom, time and space don't really exist. So you could argue, even though it probably expands, contracts, and then forms a new universe from the same, whatever you want to call the beginning of the universe is. The idea is that you could model this. It doesn't literally exist parallel, but you could model this to where all the universes are overlapping each other at the same time. Some of them exist and stop existing, but restart as a new universe. Or they go off on a tangent, stop existing, and you literally have a timeline or a time-space line where things stop working. They snuff themselves out. And those might be very common. So as the universe is arranging itself in the first, we don't even know how short of a time, these numbers would essentially pop into existence as matter coalesced from energy. Now, some claim that the number has changed in the past 2 billion years by, and this is a claim or assertion or an experiment, by 45 parts per billion of change, which is tiny. But then they also said that this finding is probably accurate to within plus or minus 20%. Which at that point I'm just like, can't tell if it was a joke. It means plus or minus 20% of 45 parts per billion. So it could be 60 parts per billion, or maybe 30, that sort of thing. Or some other number like that. Actually, it would be, about a little over 30. Anyway, is there an experimental test to see if there's any variation? Of course, this is the part where everybody gets disappointed because there's always something. The hyperfine transition in neutral hydrogen is 21 centimeters, not millimeters, not 5G. Now, what is this? This is the hyperfine transition that's used on the plaque that was sent into space on the Voyager probe. It's an indication of something that is actually a time constant. Okay, now here's the part where we're talking about a time constant in a universe that's been expanding and altering itself that may have different ways of time and space working in the past. This is the presumption. We don't assume that it's been stable throughout time. But if we make that assumption for a model, actually almost everything we see works except right after the Big Bang. So that's why we're fairly confident that works. And if you throw a monkey wrench in it by altering time-space, it still works, and it actually explains away a couple of things that we kind of understand, but really make it more likely. So it's highly likely, highly likely in this case is like 0.0001%, that time-space has not been linear, at least not completely. So this hyperfine transition of neutral hydrogen, if it was stable in time-space at the time, a long time ago, in the early universe, this leaves a unique absorption line imprint on the cosmic background radiation that you can pick up, and allows us to measure the value by looking at that ratio, because that does expose the ratio. Now here's the problem. You have to get the estimate for the age of the universe very, very close to accurate. Anyway, the problem with this is in order to do that, to test out your C-137 experimental testing, you'd have to make a 100-kilometer across antenna collector array and have it work perfectly for several years to do the experiment. It's technically possible to test the theory, but practically impossible. Thanks for watching. Have a good day. Good luck with that. Zorp.